The quantum Hall effect is a fascinating phenomenon that occurs in very specific conditions, leading to the quantization of the Hall resistance with extraordinary precision. Quantum Hall effect has earned 2 separate Nobel Prizes, one for the integer version, and another for the even weirder fractional version. The classical Hall effect was discovered by Edwin Hall in 1879. Describes the generation of a transverse voltage across a conductor carrying an electric current when subjected to a perpendicular magnetic field, used for characterizing materials and understanding the nature of charge carriers. In this figure we see how the deflection of the moving charge carriers due to the Lorentz force results in an accumulation of charge on one face of the conductor and a depletion of charge on the opposite face. For negatively charged electrons, this accumulation occurs on one side, while for positively charged holes, it occurs on the other. This separation of charge establishes a transverse Hall voltage across the conductor, perpendicular to both the current and the magnetic field. Over a century later, under extreme conditions of low temperatures and strong magnetic fields, a remarkable quantum mechanical counterpart to the classical Hall effect was discovered, revealing striking quantum behavior in 2-dimensional electron systems. The quantum Hall effect is observed in a special type of system, where electrons are confined to move in only 2 dimensions, like on a very thin sheet. This is often achieved in semiconductor heterostructures, such as at the interface between gallium arsenide and aluminium gallium arsenide, or in materials like graphene. To observe the quantum Hall effect, we need to cool these 2D electron system materials to extremely low temperatures, typically just a few degrees above absolute zero, below 4.2 Kelvin and often much lower. We also need to apply a very strong magnetic field perpendicular to the 2D plane of the electrons, around 1 to 10 Tesla. Under this strong magnetic field, the energy of the electrons in the 2D electron system becomes quantized into discrete levels, called Landau levels. This is a quantum mechanical effect, where the electrons can only occupy specific energy values. Figure shows the plot of energy of electrons versus real space position, kept under magnetic field. Each Landau level can hold a large number of electrons, and the energy difference between these levels depends on the strength of the magnetic field. When we pass an electric current through the 2D electron system and measure the resistance perpendicular to the current flow, we observe a surprising phenomenon. Instead of the Hall resistance changing smoothly with the magnetic field, it forms a series of flat steps, or plateaus, showing the quantized Hall resistance. Values of these plateaus are incredibly precise and are given by the formula Hall resistance equals to H over nu times E square in units of ohm, where nu is an integer. This means the resistance is quantized in integer multiples of fundamental quantity, H by E square. The graph shows resistivities of the quantum Hall system as functions of the magnetic field. In the graph, red line shows the longitudinal resistivity. It is 0 as long as Hall resistivity stays on a plateau level, and spikes whenever Hall resistivity changes from one plateau to the next. Green line denotes the Hall resistivity. It takes on a plateau form, therefore it is constant over a range of magnetic fields. Classically, green line looks straight with constant slope. No plateaus meaning no quantization. The resistance measured along the direction of current flow. The longitudinal resistance drops to almost 0. This indicates that the current is flowing without any energy loss, primarily along the edges of the 2D electron sample in special channels called edge states. At even lower temperatures and higher magnetic fields, another remarkable phenomenon occurs: the fractional quantum Hall effect. In this case, you see even more plateaus in the Hall resistance, but now at fractional values of nu, like 1/3, 2/5, 3/7 in the formula of Hall resistance. The fractional quantum Hall effect arises due to strong interactions between the electrons, leading to the formation of exotic quasiparticles with fractional electric charge, like E/3. The quantum Hall effect is a manifestation of quantum mechanics in the macroscopic world, where the resistance of a two-dimensional electron system in extreme conditions becomes precisely quantized due to the formation of Landau levels. In the fractional case, due to strong electron-electron interactions. Also note that resistance quantization observed is purely universal.